This week, leading up to Earth Day, we're diving into a stunning scientific development that's sending shockwaves through the geologic community, a hidden threat stirring deep beneath the Colorado River. Winding through ancient canyons and sculpted rock layers, the Colorado River has always told a silent story of time. But now, scientists have discovered a new chapter, one they never expected. What began as a routine geological survey in the Grand Canyon corridor quickly turned into an urgent investigation. While mapping sediment patterns, researchers stumbled on seismic imaging data that revealed something astonishing beneath the riverbed. A massive, previously undetected magma chamber, alive and expanding. Before we get into the details, don't forget to like and subscribe for more updates on this unfolding story. This magma body, buried some 25 kilometers below the surface, lies in a region long considered geologically stable. But new readings tell a different story. Heat signatures, shifting rock layers, and deformation patterns suggest something is happening down there. Something big. Adding to the concern are pressure anomalies picked up by borehole sensors. These shifts in underground stress may signal the beginning of heightened geothermal activity. This isn't just a scientific curiosity. It's a discovery with far-reaching implications. The Colorado River isn't just iconic, it's essential. It supplies water to nearly 40 million people across 7 U.S. states and supports vast agricultural systems and hydropower infrastructure. Any disruption beneath its flow could ripple through our environment, economy, and daily lives. It all started months ago when satellite radar detected a slight but persistent uplift near the Glen Canyon area. Just a few millimeters per year, enough to raise eyebrows, but not alarms. That changed when scientists cross-checked the data with thermal imaging and seismic activity. A clear pattern emerged, one that couldn't be ignored. Low-magnitude quakes began clustering in the area. These weren't typical earthquakes. They were shallow, highly localized, and likely triggered by rising fluids and fracturing rock. Gravimeters recorded a decrease in subsurface density, hinting that lighter, molten material was replacing older, denser rock. The signs, uplift, heat, tremors, and gravity shifts, painted a clear and unsettling picture. Magma is moving, and it's moving in a place where no known volcanic system exists. That's what led to the USGS issuing a rare red alert. Along with university research teams, they designated the region as one of elevated magmatic concern. That label isn't given lightly. It means the activity could accelerate, and that we're in largely uncharted territory. At first glance, the idea of volcanic activity beneath the Colorado River might sound far-fetched. This region isn't known for lava flows or eruptions. Its landscape was carved by uplift and erosion, not molten rock. But deeper investigations reveal a more complex picture. The Earth's crust here is thinner, sitting above a mantle zone rich in gases and fluids that reduce the melting point of rock, making magma formation possible in ways we didn't expect. Interestingly, historical data, now being revisited with a new sense of urgency, suggests that the Colorado Plateau has experienced volcanic activity before. Though it happened millions of years ago, ancient lava flows and basalt dikes scattered across the region are strong evidence that magma has surged through this land in the distant past, even if no human civilization was around to witness it. Now, scientists are entertaining a possibility once thought far-fetched, that a brand new magmatic system could be taking shape. Not a reawakening of an extinct volcano, but the slow birth of one, still forming deep beneath the Earth's surface. This unfolding discovery is rewriting what we thought we knew about the geology of the American Southwest. Research teams are working around the clock, using cutting-edge tools like muon tomography, a technique that harnesses cosmic rays to generate detailed 3D scans of underground formations. So far, the early models reveal something startling. The magma chamber isn't just rising. It's spreading sideways too, hinting that it may be feeding from a much broader anomaly deep within the Earth's mantle. What's even more concerning is the location. Two critical pieces of infrastructure, the Glen Canyon and Hoover dams, sit within range of the evolving zone. While there's currently no indication of an imminent eruption, scientists are watching the warning signs closely. Deformation patterns are increasing, and gas emissions, especially carbon dioxide and sulfur dioxide, are on the rise, indicating the crust is undergoing stress. These aren't the gases of an erupting volcano just yet, but they are unmistakable red flags. Active degassing is often one of the earliest clues in known cases of magmatic acceleration. To stay ahead of the situation, Dozens of new monitoring stations have been deployed across the region. From tilt meters tracking microscopic shifts in ground angle to gas spectrometers analyzing vented emissions, every reading is fed into real-time simulation models. The goal? To figure out whether this magma body will settle, or keep rising toward shallower layers where it could come into contact with groundwater. That potential interaction is a major source of concern. When magma meets underground water sources, it can cause phreatomagmatic eruptions, violent explosions powered by steam. These eruptions don't require visible volcanoes. Even a hidden chamber flashing groundwater into vapor can crack open the crust with staggering force. What makes the Colorado River situation even more precarious is the sheer amount of water flowing directly above the zone of activity. If the magma keeps climbing, even a low-probability steam explosion could carry devastating consequences. It's a risk geologists can't ignore. There's also the threat of induced seismicity. As magma moves, it fractures rock, opens new pathways, and can even reactivate ancient fault lines. While the early tremors have been minor, the potential for stronger, more disruptive quakes increases as pressure builds. These aren't your typical tectonic earthquakes, they are volcanotectonic, driven by rising molten rock. Given the aging infrastructure in the area, and the millions of people who rely on the river, scientists are approaching this situation with a high level of caution. Even a moderate quake could disrupt essential systems or spark a chain reaction of failures. Right now, the magma is categorized as intruding but not erupting. Still, it's far from dormant. The red alert isn't meant to incite panic. It's a formal recognition that a significant geological process is unfolding in real time with an uncertain future. And that's what makes this so critical. Geology usually moves at a glacial pace, with changes too slow for humans to notice. But this is different. Thanks to advanced monitoring and data from satellites, drones, and ground instruments, scientists are watching this story unfold with unprecedented clarity and speed. Every signal matters. Every tremor, every gas spike, every subtle shift in the Earth's surface could help answer the biggest question of all. Is this just a geological blip, or the birth of something far more powerful beneath one of the most vital rivers in America? Scientists aren't just keeping an eye out for signs of an eruption, they are asking a deeper question. Why is this happening now? Some researchers believe it could be tied to larger tectonic shifts underway in the western United States. Changes in the Earth's lithospheric stress field might be reawakening ancient processes deep in the mantle. Others point to long-term climate impacts. As snowpacks shrink and water reservoirs dry up, the surface weight on the crust is decreasing. That reduced pressure could be allowing superheated fluids from deep within the Earth to rise through cracks that were once sealed shut. These are still working theories, but they reflect just how vast and complex this mystery really is. What's happening beneath the Colorado River isn't just an isolated event. It's a window into the forces that shape continents, shift hydrological systems, and remind us that even the most stable landscapes can be anything but. As data continues pouring in, from orbiting satellites, drones, and teams on the ground, each new reading adds another layer to this unfolding story. What started as a subtle bump in the Earth's crust has grown into a full-scale scientific mobilization. The goal isn't just to understand what's happening now, but to figure out what could come next. Even though the magma remains far beneath the surface, its presence is already affecting the world above. Policymakers are taking notice. Emergency response plans are being reviewed. Funding is being redirected toward urgent research. For now, the Colorado River still flows calmly through the canyon, as it has for millions of years. But just beneath that peaceful surface, something is stirring, hot, pressurized, and potentially transformative. The initial shock of discovering a rising magma body was only the beginning. In the days that followed, a bigger picture emerged, one that suggested this wasn't a one-off anomaly, but part of a wider awakening happening across the southwestern U.S. As geologists sifted through reams of data, gravity readings, heat flow maps, and the chemical makeup of gases escaping from springs, they noticed something striking. A larger pattern began to take shape, a corridor of geophysical anomalies stretching from southeastern Utah to northwestern Arizona. It had gone unnoticed for decades, simply because no one had looked at it in this way before. This zone was long considered stable, unlike the seismically active Cascades or the known volcanic fields of New Mexico. But now, something has changed. Isotopic signatures in escaping gases, especially the ratio of helium-3 to helium-4, a marker of deep mantle origin, hint that a mantle upwelling may be rising beneath the crust. Such upwellings can do more than just trigger volcanic activity. They can rewrite a region's geological identity. Unlike volcanic arcs, where magma comes from recycled crust, a mantle plume brings up raw, volatile-rich material from deep within the earth. It's hotter, more chemically active, and capable of driving long-term changes to the land above. The discovery under the Colorado River now appears to be just the tip of something much larger and more complex. It has shifted the mission from passive observation to proactive exploration. New drilling projects have already been proposed. Teams want to retrieve core samples from uplifted zones nearby, to see exactly what kinds of rocks are being transformed, and how. They are looking for signs of high-temperature metamorphism, chemical shifts, and traces of trapped volatiles. These clues could reveal the true size, depth, and potential lifespan of the anomaly, and whether we're witnessing the start of a long-lived magmatic system, or a fleeting pulse of deep earth energy that will fade over time. At the same time, a new layer of insight emerged from geoelectrical studies. Using magnetotelluric surveys, which tap into Earth's natural electromagnetic fields, researchers uncovered zones of unusually low resistivity spreading out from the suspected magma chamber. These highly conductive regions often point to the presence of partial melts or interconnected underground fluids. But what really caught scientists' attention was movement. These zones weren't fixed in place, they were slowly migrating, especially toward the northeast. That meant the magma wasn't just collecting in a single pocket. It was actively pushing outward, creeping into the surrounding crust by following hidden fault lines, ancient fractures that have existed for millions of years. Normally, those old faults lie dormant. But when under pressure from rising heat and fluid, they transform into natural conduits, allowing magma, gas, and superheated water to surge through. In essence, the magma chamber was reaching out like roots from a tree, searching for the path of least resistance. And wherever it reached, it left a mark. Temperatures beneath the surface started rising in those areas. Groundwater chemistry changed. Springs that were once cool and crystal clear began flowing warmer and carried traces of unusual minerals, arsenic, lithium, and rare earth elements, clues that deeper geothermal fluids were making contact with surface water systems. These changes weren't just underground. Local ecosystems began to show subtle signs of stress. Aquatic species in nearby springs were affected by rising temperatures. Plants that depended on shallow water tables started to show early symptoms of mineral imbalance and nutrient shifts. This type of change, where deep earth energy begins to influence surface ecosystems, is known as a magmatic interface zone. It's not as explosive or dramatic as a volcanic eruption, but it signals a slower, deeper transformation, one that reshapes both the land and the life it supports. What began as a geological anomaly has now become a topic of concern for city planners and water experts. With groundwater temperatures climbing and chemical composition shifting, new questions emerged about long-term water safety in the Colorado River Basin, a region already stretched thin by overuse and prolonged drought. If these trends continue, even slight geochemical shifts could force costly upgrades to water treatment systems or compromise the quality of drinking water in vulnerable areas. This also triggered a broader assessment of infrastructure in the region. Seismic risk models had to be updated to account for a new kind of threat, not from tectonic movement, but from pressure building inside the earth. The potential for old fault lines to reactivate meant that bridges, pipelines, and dams, including the massive Glen Canyon Dam, were now being re-evaluated with fresh urgency. Engineers began modeling scenarios once considered improbable, like minor to moderate quakes paired with slow ground deformation. What used to be hypothetical was now being worked into real-world emergency planning. Insurance companies and federal agencies quickly followed. Risk maps were redrawn. Insurance policies covering earthquake and geothermal damage were reviewed and, in many cases, rewritten. The Bureau of Reclamation launched a new review of water distribution models, preparing for the possibility of temporary disruptions to pumping stations or sediment surges triggered by seismic or subsidence activity. As engineers and hydrologists raced to understand the changes beneath the Colorado River, atmospheric scientists stepped in with their own concerns. They began detecting slight but notable changes in the air just above the river corridor. Gases like carbon dioxide and sulfur dioxide, known to be released from deep within the earth, can impact air quality well before any volcanic activity ever reaches the surface. To track these emissions, teams deployed specialized drones equipped with high-precision spectroscopic sensors. These drones followed gas trails that tend to gather in low-lying areas, where they could pose potential health risks to wildlife and humans. Though current levels remain low, the presence of these volcanogenic gases in this region is unusual, and enough to keep scientists on alert. But the story unfolding beneath the Colorado isn't just scientific. It's deeply cultural too. The land around the river holds sacred significance for many Native American tribes, including the Hopi, Navajo, and Hualapai. For generations, these communities have passed down oral traditions that speak of the earth breathing or fire beneath the stone. Long viewed as symbolic or mythological, these stories are now being revisited through a scientific lens. Geologists and anthropologists are joining forces to explore whether these ancient accounts might hold clues, echoes of past geothermal events embedded in memory and myth. Some tribal elders recall warm patches of ground or springs that suddenly dried up and grew hot, details that may line up with past thermal anomalies. This fusion of indigenous wisdom and modern science is creating a powerful new framework for understanding Earth's long-term geological cycles. By listening to these stories and honoring their relevance, researchers are expanding their datasets and enriching the scientific narrative with a deeper human connection. From shifting groundwater chemistry to intergenerational memory, every piece of this puzzle is adding to a broader, more multidimensional picture. What began as the discovery of a single magma body has evolved into a complex investigation involving everything from geophysics to cultural heritage. It's a stark reminder that the Earth's interior isn't separate from life above. It's constantly shaping it, often quietly, until one day that influence breaks the surface. Right now, the magma remains buried deep underground, its movement slow and subtle, measured in centimeters and pressure gradients. But even without an eruption, it's already pushing against the crust, prompting questions, policies, and preparations across multiple fields. Where this will lead is still uncertain. The magma could stabilize, it could grow, or it might take new, unpredictable paths underground. That's the nature of geology. It speaks in signals, small, scattered pieces of a story still unfolding. To better understand what's happening, scientists have launched several major initiatives. FEIST, a new network of underground observatories, is being built. Backed by a mix of public and private funding, this system combines seismic and thermal sensors with AI-powered pattern recognition. Advanced algorithms are now combing through millions of data points, looking for signs of acceleration or shifting flow paths that human eyes might miss. Second, researchers are conducting controlled seismic experiments. These tests help map out the exact shape and structure of the magma body, revealing where rock may be nearing its breaking point, an early warning for potential future activity. Third, breakthroughs in real-time simulation have opened up powerful new modeling capabilities. Using the freshest data, scientists are running dynamic scenarios, ranging from slow, steady intrusion to sudden, steam-driven eruptions. These models don't just forecast outcomes, they help pinpoint what signs to monitor, what regions are most vulnerable, and how quickly systems would need to respond if things escalate. If you enjoyed this deep dive into the Colorado River mystery, give us a like and subscribe for more science-driven updates. Got thoughts or theories of your own? Drop them in the comments. We'd love to hear what you think could be hiding beneath the riverbed. Thanks for watching, and we'll see you next time.